This is the video on GCSE vectors. If you're watching this video, you've probably been given a homework to do over Easter on vectors, and hopefully this video will give you the information you need to answer the questions on that homework. So we're going to start from the basics and talk about what a vector actually is and how to write a vector, how to notate it. Then we're going to move on to actually solving questions, so finding the vector between 2 points. We're also going to talk about how you can distinguish parallel vectors and solve harder problems where midpoints of lines are involved. The purpose of this video is to let you work at your own pace. So if there's something you don't quite understand, pause, rewind, go over it again. I will explain things thoroughly, but obviously everyone works at a slightly different pace. Now, you will have recently been doing work on transformations, and in particular I want to look at translations. Now a translation is just when we move a shape. So let's just take this shape and move it over here. Now we're interested in which direction it's moved in and how far it has gone. We can draw a little line on our grid which shows us the direction it's moved in and how far it has gone, and we can show that with a little arrow. Now that is how we would draw a vector on a grid. And how would we write down the vector? This is something you will have done before. We can say that it's moved 1, 2, 3 spaces in the x direction and 1, 2 spaces in the y direction, and we would write 3, 2. That is our vector. It's moved 3 spaces to the right and 2 spaces up. And that is what a vector is. It tells us which direction we've gone in and how far in that direction we have gone. Now I've drawn the vector there, but we could have also drawn it between the 2 equivalent points on any part of that shape. So those all give us the same vector. And like I said, we show it on a grid with a straight line and an arrow. So each of those vectors is the vector 3, 2. Let's do another one. So if we now translated this shape over here, let's draw in a vector. So let's just go from this corner to the same corner on the image of the shape. So we're going in this direction. So really important you put arrows on these lines, because otherwise they're just lines, they're not vectors. Now this vector is going 1, 2, 3, 4 to the left, and left is the negative x direction, so we would say it's minus 4, and it's gone 1 up. Well, up is the positive y direction, so it's just a positive 1. So that blue vector is the vector minus 4, 1. Okay, so what we've said is a vector has a size, a vector has a size and a direction. Okay, now this is different to numbers that we've used before. If we have a look at this square over here, then what we would usually do if we didn't know the length of each side of the square, we would just call it x or y or z, and these letters tell us that there's a number there which we don't know yet. Now, in a square, if that size of that side of the square is x, then the size of this side of the square is x, because they are the same size. So we would call both of those sides x. If we look over at this square, if instead of using these numbers, which we call scalars, and scalars are just numbers with no direction. So over here we didn't care which direction we were going in. That x is the same as that x. It doesn't matter that the lines are going in different directions. But with vectors, we do care about the direction, and we have to show which direction we're going in with an arrow. So if we call this line A, and we say that A is going from left to right, then we can also call this line A as well, as long as it's going from left to right. But this line, even though it's the same size, it has got a different direction. The direction of this line is going from the bottom upwards, whereas the direction of our vector A was going from left to right. So this is a different vector, so we can't call it A, so let's give it a different letter and call it B. And that is the main difference between scalars and vectors. The fact that a vector has got a direction. And the way when we write them down, to show that something's a vector and not a scalar, we'd underline it like this. And that shows us that we're dealing with vectors, not scalars. So the vector A goes from left to right, and however long that line is, that's its size. B has got the same size as vector A, but because it goes in a different direction, it's got a different vector. We use a different letter for it. In the same way, if two vectors were going in the same direction, but they have different sizes, they're not quite the same vector, but they would be parallel, and we're going to come on to parallel vectors a little bit later. Now if I go back to a grid and I draw some vector on that grid, so let's draw a vector that looks like that, yes, okay. And let's say that that goes in between the 2 points A and B. So when I'm marking down points on a diagram, I use capital letters. Okay, so you should have seen that before when we're marking down points on a circle or points on a parallelogram. We use capital letters. Now, the vector from A to B, and the way we would write that is we'd say we want the vector going from A to B, so we'd put both the points down and an arrow in between showing that we're going from A to B. That vector is going to be 1, 2, 3, 4, 5, 6 in the x direction, and 1, 2, 3 in the y direction. So that vector is 6, 3. Let's do another vector. And let's say that this goes in between the points C and D. Now the length of the size of this vector is 1, 2, 3, 4 in the x direction, okay? 4 in the x direction, and 1, 2, 3, 4, 5, 6 in the negative y direction. So one more time, 1, 2, 3, 4 to the right. So 4 to the right, 4 in the x direction, so we write a 4 down here. And 1, 2, 3, 4, 5, 6 down. And because it's down, it's negative, because down is the negative y direction. Okay, so there we've got two vectors, and we can see which direction they're going in, and we know what size they are. And we can write those vectors down using the numbers in brackets like I've shown. Right, but what about if we didn't have the grid? Well, if we didn't have the grid, then we don't know how far across and how far down or up these vectors are going. So I need to get rid of the numbers. These are now unknown vectors to us. And just like in algebra, when we have a number we don't know, we give it a letter like x or y. We do the same thing with vectors. And the most common letters we use are A and B. Obviously making sure we underline them. So we could call this vector vector A, and this vector we could call vector B. And in that case then, C to D is going to be equal to vector B, whatever vector B is. It's just something we don't know yet. Okay, but we might be able to find it out in the question, or like in other algebra questions, we might just have to leave our answer with the letters in. Let's look at quite a straightforward exam question. So we've got a point P which is marked on the diagram, and it shows us that we've got two vectors, vector A, which is basically just two squares to the right, two spaces to the right, and a vector B, which is 1, 2, 3 squares to the right and 1 square up. Now there's another point Q somewhere which we need to draw in, because we want to find out, we want to show that the vector PQ is equal to A plus 2B. So there's another point Q somewhere, and the line that joins P with Q is going to have the vector A plus 2B. Okay, well if we start at P and we think, well, first of all, P goes a vector A. Well, a vector A would be 2 squares to the right. That's what vector A is, which we can see over here. That's vector A. But it also goes to B. Now a vector B looks like this. It goes 3 across and 1 up. So that would be 1B. 3 across, 1 up. That would be 2B. So altogether, that P is going 2 to the right and 1, 2, 3, 4, 5, 6 squares across and 2 squares up, because it's 2 times what we know B is. So that's where the point Q would be. That's where the point Q would be. And to draw the actual vector in, the vector from P to Q, we just want one straight line. So we need to draw the vector P to Q in like that. So a straight line going from P to Q, and we put a little arrow on there like that. And we could say that that vector is the vector A plus 2B, because that's what we've worked it out to be. Okay, here we've got a grid with lots of different points on. Okay, so I was saying that to show a point on a diagram, we use a capital letter. Well, here we've got lots of different points, all connected with different lines. Now you can see down here that we've drawn 2 vectors in. Now, just to mix it up, I'm going to call this vector vector K. And remember to underline it because it is a vector. And I'm going to call this vector vector M. And I'm going to underline that. Okay, now you can see that the vector K is that big and it goes in this direction, the direction of the arrow. Well, you can clearly see that that's the same size as O, the point O, to point A. And that's also in the same direction, which means that the point O to A is also vector K, because a vector needs a size and a direction, and you can see that the point O to A has the same size and the same direction as vector K, so it must be equal to vector K. Vector M goes vertically upwards, and it's as big as you can see it here on the diagram. It's the same size as vector O to B, and O to B is also going in the same direction, vertically upwards, which means that the vector O to B is also equal to n. Now you can probably find lots of other different vectors between points which have the same values. For example, the vector K to P. The vector K to P also has the same size and direction as vector M. So KP also is vector M, because it is the same vector. It doesn't matter where on the diagram it is, all that matters is that it's going in the same direction and it's got the same size. Okay, how would we find though a vector, let's say, between B and H? Okay, now the vector from B to H is going in a different direction to the other vectors that we know. So we know M and we know K, and we know what direction they have and we know how big they are. But B to H is going in a different direction. But the thing is, we just basically want to get from point B to point H. It doesn't matter how we do that. So, to go from B to H, I could go from B to E, and then E to H. I've taken a different route, but I've still made the same journey. I've still reached the same destination. So, B to H is the same as going from B to E and then E to H? Well, B to E I can clearly see is the same as my vector M over here. So that's vector M, and E to H is the same as my vector K. So I'm adding on my vector K. So just like in that exam question we had, where the vector P to Q was a combination of vectors, the vector B to H is also a combination of two different vectors. And that's fine. Just like in algebra, these are different terms. They're not like terms, so we can't collect them together. So we just leave our answer as M plus K. Right, let's just look at another one. Okay, so let's look at the vector A to T. Okay, so you can clearly see that this is a lot bigger in size than the other vectors we've been looking at. Now A to T, I can't go there directly because I don't know what direction that vector is yet. Some of the quicker ones among you might notice something about the direction it's going in, but that's something I want to come back to later. Now A to T, I'm not going to go directly there. I'm going to go from A to M, and then from M to T. I'm going to go in that direction, like that. So, A to T is the same as going from A to M, and then adding on M to T. Now A to M is just 3 lots of the vector M, okay? Because it's going in the same direction, but it's just 3 times as big. So I could do M plus M plus M, or I could just say that there's 3 lots of the vector M. M to T is the same sort of idea. It's 3 lots of the vector K. So I'm going to add on 3 lots of vector K. Okay, and that's what the vector A to T is. 3M plus 3K. And that's basically how you find vectors between 2 points. You just have to look at the vectors that you've already got and try and use them, combine them in different ways until you can get from the point you're starting at to the point you want to get to. And just one important thing to note is that we can choose any route to get from one point to another. So to get from A to T, I decided to go from A to M and then from M to T. But I could have gone A to J and then J to T, because A to J would have been 3K and J to T would have been 3M. So I would have got 3K plus 3M, which is the same as 3M plus 3K. I could have also gone A to C to G to K to P to R to S. It's a little bit more haphazard, but let's see if we get the same thing. A to C is K. C to G is M. G to K is K. K to P, is M. P to R is K, and R to T is M. And if I simplify all of that, collecting the like terms, that is equal to 3M plus 3K, which is equal to what I've already got for AT. So you can see that it doesn't matter which way we go in, as long as we get to where we need to get to. So if you want to make a note of that, we can choose any route to get from one point to another. And now you should be in a position where you can have a go at task A on your homework.